And our last presentation of this session will be an online presentation, recommendation on live streaming platforms, dynamic availability, and repeat consumption by Jérémie Rappaz.
Thank you so much. Hello everyone, my name is Jérémie Rappaz, and today we'll discuss a work called Recommendation on Live Streaming Platforms, Dynamic Availability and Repeat Consumption. And this is joint work with Julian and McAuley from UCSD and Karl from EPFL. So I believe many of you are familiar with live streaming platforms nowadays. Those are popular web services where people can record and broadcast their activity on a computer in real time on the web. So of course they became really popular with video game communities, but now expanded to wider audiences. And you might know some of the names there: Twitch, Mixer, YouTube Live. Those have really become popular. Twitch last year reported 50 million daily users and 3 million monthly broadcasters. So the rise of those new way of broadcasting content raise question in terms of how do we manage this kind of content and what does it mean for recommender system communities. And in particular, what I believe is really interesting in such services is the fact that items are highly dynamic. So in our work, we chose to represent items as streamers. So this is the equivalent of a TV channel. And channels are not constantly broadcasting content, right? So you might have a few items there and a few discrete time steps. And at every time step, there is only a subset of available that is a subset of item that is available for item to consume. So when a user logs in, he's exposed to a limited selection of items, and then he will consume one of them. So in this example, we consider this as a positive example. He will click on a channel and watch some content. So the question that we are asking in this work is how to make recommendation when availability is dynamic, how to train from such data, and how to effectively make recommendations. So we assume to be in a setting, in a ranking setting, and so we learn from pairs of samples, right, like a positive and a negative sample. And we observe some available item at any time step. So for example, here, item 1, 3, and 4 are available. And so the obvious option would be to apply existing technique, right? So basically we will learn from a positive example that we observe and a negative example that is sampled from the full set of items that we ever observe in our data sets. But the problem with that is that this negative interaction could mean that the positive item was indeed preferred over the negative, but it could also mean that the item was unavailable at that point in time. So an obvious improvement over option 1 is to sample a negative item in the set of available item, right? So we make them all availability aware through sampling, and we restrict the model to learn from valid option exclusively. And we'll see how this performs. But we wanted to go a bit further in this work, and the question that we're asking is, do we gain something from learning from the full context of availability? So if we observe everything that is available at any point in time, can we learn something from this to better predict user action? And so the objective, if we can do this, is to learn dependencies among available items. So just a quick, a very quick point. We cast this problem as a sequential recommendation task. We use an off-the-shelf recommendation method, Absract, that basically pulls information, important information from the sequence and create a sequence vector that represents the user history, right? So, but our framework is not tied to this particular framework. We can use BERT4rec or anything else. Now, as I was saying, we want to learn from availability context. We want to learn from items that are available on the platform at any point in time. And we represent this set A of T, which is a set of items that are available. The problem is that this set is generally very large. So the solution that we found is that we will basically embed all the items that are available at this point in time and rank them using the sequence vector that we created from that we obtained from the sequence encoder using a dot product operation, right? So this creates basically a top K selection of a potentially good candidate item. Then, as I was saying, we want to learn relationship among those items. So to give you an example, this could mean that when a popular streamer starts broadcasting content on his channel, we want the model to be able to modify its prediction for other items. So we solve this problem by using an attention module, which works the same as Absract. Basically, it's a query key value attention module that learns dependencies among items. And it has the same dimensionality as in the input and in the output. So we basically only sort of infuse the knowledge of what's available currently into each of the individual vectors. And so we use this sequence vector for this pre-candidate selection phase, let's say, and also for the final ranking, which makes the approach end-to-end. Now, another interesting specificity of live streaming platform, and especially if we consider items as a channel, is the fact that we have to model repeat consumption, because user will consume content from the same channel multiple times, right? And so in order to give a bit more signal to the model to distinguish between those options, we wanted to add temporal dynamics. So what you can see here is a distribution, a density distribution of time intervals between two subsequent consumption of the same channel by the same user, right? And what you can observe is that there is a clear 24-hour cycle, because people consume things more or less at the same time during the day, but also that there is a bit more density on the left side of the figure, which means a bit more density for shorter frequencies. And regardless of what it means, we wanted to learn from this kind of distribution. So we solved this problem by dividing this distribution into bins of 24 hours, and each of the bin will have its own embedding vector attached that we learned during training. So in practice, how we incorporate this is that we take all the candidate vectors that we identified previously, and we look at when those candidates appear in the interaction sequence, okay? And we measure this time interval, we embed this time interval with an embedding matrix, and we add them on top of the candidate vector with an addition. So the goal here is basically to give the attention module some ability to learn from item semantics, but also temporal dynamics. And so I haven't discussed about the dataset yet, but we collected a pretty large dataset from Twitch. And basically, we took a full snapshot of all available stream every 10 minutes during 43 days. This was a pretty large crawl. And for each stream, we retrieve all logged in users from the chat. So the full dataset contains more than 100 million interaction, and we created a smaller benchmark version for evaluation purposes. And so the results, so this is only a glimpse of the result table. I wanted to focus on the option I described, but the results are much more in depth in the paper. And so if we go back to our option one, that's negative sample uniformly over all possible items, and we only use a sequence encoder. Those are the performance in terms of hits at 1 and hits at 10. And you can see that by only sampling available option at interaction time, we can obtain a much better performance. So if you need to remember like a quick trick to improve your model for this kind of setting, this is the one. And now the two, let's say, contribution that are incorporated into the model, so the attention module over available option and the temporal embeddings both provide an improved performance individually, but also combine and provide the best observed score, which means that the attention can really learn from the temporal information. And so in the paper, we have a much bigger discussion we measure, basically, we distinguish between novel interaction and repeated interaction, but I skip this for brevity here. And so in conclusion, what we learned from designing a system in this setting is that learning from available option is very important. So you need to sort of mimic this in your training setting. Learning dependencies among available items seem to help, and modeling repeat consumption is also important if you're considering items as channels. And so we identify some more interesting aspects in our data set. So for example, we identify bursts of activity that might be interesting to look at around specific channels, and also modeling content is something we haven't touched yet. So everything is available there in my GitHub repository. Thank you very much for your attention, and I'm happy to take questions.
Thank you for your presentation. There are, I see, a few online questions. If there are any questions from the room, please approach to the microphone. So I will start with my question first. I was thinking about the repeat consumption. So have you considered the contextual information when actually looking into the repeat consumption? For example, if it's a holiday period, maybe people have more time to watch things over, like to follow things over time. So have you looked at this contextual aspect, or are you planning to look into?
So thank you very much for the question. It's a very good question. Now, you're describing sort of seasonality aspect of the data, and we only have 43 days of data, right? So this is pretty short term. And of course, the idea of modeling time interval was to identify as much signal as we could to distinguish among repeated interaction with the same item. Now, of course, I mean, incorporating more information will probably help, because the problem is that if we consider an item as a channel, you don't have a lot of information, right? Because people will repeatedly consume it, and you don't really know in which context. So context definitely help, and there we used temporal embedding, but for sure, the more the better. I just want to add something, because I think it's important there. We choose as a design choice to select channels as item, but there is another alternative, which will be to consider item as streams, so short segment of video, and in that case, you wouldn't be exposed to this problem of repeat consumption, but in the problem of extreme sparsity, or you will have to deal with content. So future research could also look at this alternative.
Okay, thank you. There are a lot of online questions. I will just read one. What were your criteria when you created a benchmark data set?
To sample it as, how to put that? We sampled 100K users at random, and that's it. We wanted the procedure to be simple, so that's it. Yeah, I guess if I remember correctly, we selected user with at least maybe at least 3 interaction or something like that, but that's it.
Okay, thank you. There are many interesting questions online, so please, for all the authors, please check the RecSys Hub for further discussion and questions. Thank you very much for your presentation, and thank you all for participating. So now it's time for a break.